All right, ladies and gentlemen, back to ionization energy. Recall that ionization energy is the energy needed to remove an electron. So basically, the more the nucleus is pulling that electron in, the harder it is to remove. So it goes a bit like the atomic radius thing. So once again, we got beryllium. Okay, so we're going to go back to the periodic table. Where's beryllium? Beryllium is right here. Okay, so we're going to go all the way to the end of the period, and we're going to go neon again. Neon has 10 protons. All right, so here we go. So for neon, neon has 10 protons, so a positive 10 in the nucleus. And so it's going to have the 10 electrons. Just like that. Now, we had a positive 4 here. So there's a relatively large attractive force, but this is a positive 10. So that is a much bigger attractive force than the positive 4. So we have this large attractive force pulling the nucleus together with the valence electrons on the outside. So that large attractive force is attracting every one of those electrons, making them more difficult to remove. So you had a larger attractive force here, making it more difficult to remove those electrons. So, as we go across, ionization energy goes from relatively small, and then it gets bigger and bigger and bigger. So the ionization energy across a period ionization energy increases, becomes more difficult, and takes more energy to remove an electron. All right, now, just like on the last one, I'm going to switch to green so you can see the difference between these. All right, so it increases, and that's because across the period, you have a larger positive charge in the nucleus with more attraction to the valence electrons. So it takes more energy, ionization energy, to remove one. And that is why ionization energy increases across a period.